so we're going to discuss solution to exact equations. So let's have first the definition of exact equation. Consider the first order and first degree differential equation m dx plus n dy equals 0. The equation is said to be exact if there exists a function f which is a function of x and y such that the partial derivative of m with respect to x is equal to m and the partial derivative of f with respect to y is equal to the function n. Differentiating m with respect to y and then n with respect to x, we will obtain the equation the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. So take note that this is a necessary and sufficient condition for the exactness of the equation. And the function f is the solution to the exact equation. Now there are three ways to solve exact equation. So the first method is using the following partial derivatives coming from the definition of exact equation, that the partial derivative of m with respect to x is equal to m and the partial derivative of f with respect to y is equal to m. And the function f here is the solution to the differential equation. So let's have an example. So we try to solve 2xy minus tangent y dx plus x squared minus x secant squared y dy equals 0. So we'll take this as our m. And then this one is your function n. And then we first test for the exactness of the equation. Determine if the equation is exact by getting the partial derivative of m with respect to y. So in this case, x will be treated as constant. So 2xy is constant, so copy. Derivative of y is 1. And minus derivative of tangent is secant squared y. And then the partial derivative of n with respect to x, so here your y is constant. So derivative of x is 2x. And then secant squared y is constant, so you just copy. Derivative of x is 1. And as you can see, the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x, and therefore the equation is exact. Okay, so either we use the first equation or the second equation to find the function f. So starting with the first equation of partial derivative of f with respect to x is equal to m, and then if we try to solve for f integrating, we get integral of df is f, so that is equal to the integral of m dx. And then this is our function m from the differential equation. So we integrate partially with respect to x, so we treat y to be constant. Okay, so integrating, okay, so 2y will be constant. Okay, copy. And then integral of x is x squared over 2. tangent y minus tangent y is constant. So, integral ng constant is constant times x, no, with respect to x. Since we treated y as constant, then your constant of integration will be possibly, no, q of y. And then simplifying, that will be your f is x tangent y plus q of y. So we need to find now the function q of y using the second equation. Okay, so the second equation tells us that we get the derivative of f with respect to y, and then we will equate that to the function n. So integrating this, okay, this function of f, so rather differentiating now with respect to y, so x here will be constant. Okay, so x squared is constant, so copy. Derivative of y is 1. X is constant, so copy. Derivative of tangent y is secant squared y. Derivative of q of y, so we will represent it by q prime of y, and then equate to n. So this is our n from the differential equation, and equating the two, no, yung x squared will cancel out. We're solving for q prime, no? Also x secant squared y, and that gives us q prime of y equals 0. And if this is to get q of y, we integrate, so get integrating 0, that will be constant, and therefore if q of y will be 0, then your f is just x squared minus x tangent y plus constant. So this will be your general solution. Okay, the second method is using the line integral. So we have two versions. This is the first form, no? We integrate from 0 to x the function mxy dx, and then integrate from 0 to y the function n0y. So from nxy you equate or substitute x equals 0, and this will be the resulting function will be your n of 0y. And then in the second form, from mxy you replace y by 0, okay, and then retain the function n of xy, provided that using these two line integrals m and n should be continuous, no, at x equals 0 and y equals 0. Okay, so let's solve the same equation. Okay, so we use the first form of the line integral. So we just copy m, then here we set x equals 0, but take note that when x is equal to 0, this will be equal to 0, no? Everything will be 0. Okay, so what is left is 2xy and tangent y, and then integrating partially with respect to x, so y will be constant, so we copy 2y, okay, and then integrate x, that will be x squared over 2. Tangent y is constant, so integrate with respect to x is constant times x. Then substitute the limits from 0 to x. In this case, we have xx here, tapos 0, so minus 0. You still get the same expression, so therefore this is your general solution. same as the answer in example number 1. Okay, if you try the other form, so in this case y will be 0, and then everything here will be 0. Okay, and then you retain the right hand side. Okay, and then the third one is finding the exact integrable or the exact differential in the differential equation, and then apply integrable combination. So expanding the equation, we get the following: 2xy dx minus tangent y dx, x squared dy, and then minus x secant squared y dy equals 0. And then look for terms, okay, that are exact differential. For example, the 2xy dx, x squared dy. If you get the derivative of y here, that gives you dy, and then if you get the derivative of x squared, that will give you 2x dx, and therefore the two terms are exact differential by inspection and can be written as derivative of x squared y. Okay, in the remaining two terms, derivative of tangent y is secant squared y dy. Derivative of x is dx, and therefore these two terms are exact differential and therefore can be written as derivative of x tangent y. And then you can factor out negative here. Okay, so therefore the equation can now be replaced, okay, by integral of dx squared y minus integral of dx tangent y, and take note that derivative of u, or rather the integral of du, is equal to u. So therefore the integral of derivative of x squared y is x squared y. The derivative of x tangent y is x tangent y. Therefore this is your general solution. Okay, so let's try another example. But in this example, this is your m, okay, m dx, so this will be your n dy. Okay, we test for exactness. So the derivative of the partial derivative of m with respect to y, okay, x will be constant, so copy 2 cosine x sine x, and derivative of y squared is 2y, so you get 4y cosine x sine x, and then cosine x is constant, derivative of y is 1. Partial derivative of n with respect to x, so y is constant, derivative of sine is cosine, minus 2y is constant, okay, then times the derivative of cosine squared, so you get here 2y, copy, and then derivative of cosine squared, so apply power rule, so that will be 2 cosine x, okay, 2 minus 1, so the power is 1, then derivative of cosine x is negative sine x, so applying the power rule, and that gives you positive, okay, positive, negative, so positive 4y cosine x sine x, and therefore the equation is exact, satisfying this condition. Okay, and then expanding, Okay, we expand the whole equation, no? And then look for exact differential. Derivative, so these two are exact differential because derivative of sine is cosine dx, derivative of y is dy, and therefore that can be combined as derivative of y sine x. Okay, now the other two terms, okay, so you have cosine cosine squared, no, cosine squared x. So cosine squared x, the derivative will be 2. Cosine x, then derivative of cosine x is negative sine x. So we include negative here. So we have negative cosine squared x. And then the derivative of the derivative of y squared is equal to 2y dy, and therefore the two terms are exact differential and can be combined as negative y squared cosine x squared. So we can now replace the equation by these two integral combination. So the solution will be y sine x minus y squared cosine squared x dx. Now, if we'll be using the line integral for the same equation, okay.
It's 2 o'clock.
Okay, so using this line integral, y here is equal to 0. By the way, this is your m, this is your n. Okay, so m dx plus n dy. So when y is equal to 0 here, everything will be 0. Okay, so everything will be 0. And then you have n xy, so sine x, and then minus 2y cosine squared x. And then integrate partially with respect to y, so therefore x is constant, so sine x is constant, so copy integral of y, integral of constant is y times constant, integral of y squared is y squared over 2, so 2 will just cancel out here. Cosine squared x is constant, so you just copy. Okay, and then substituting the limits, so y minus 0 0, so you get the same equation, y sine x minus y squared cosine squared x equals c.